Good afternoon, ladies and gentlemen. Welcome to another exciting episode of Dave Does Math from Home. I am especially enthusiastic about today's episode. Today we are talking about the chain rule, which in addition to being super cool by itself, is also just a huge part of why calculus works the way it does. So once we finish this section, we're going to be able to sort of go back and look at some of the other calculus stuff that we've done before, and hopefully it's going to make a lot more sense. We're going to be able to start writing it and thinking about it in a new way that, again, I hope is more clear. It's like a gateway to a lot of much more interesting topics that I'm excited to talk about. So, without further ado, the chain rule. Quick review. We've talked about how, when you're taking derivatives, addition, subtraction, coefficients are all safe. Multiplication, division, and composition are not safe. So, for addition, subtraction, coefficients, you don't need any special rules. They just sort of behave in the intuitive way you would expect them to behave, and all is well. For multiplication, we have the product rule. For division, we have the quotient rule. And for composition, we have the chain rule. So, we're going to explore how the chain rule works a little bit, similar to how we explored the product rule when we first introduced that. And then when we have a pretty good handle on what the chain rule says, we'll do some more exciting examples. Let's start with something f of x equals x cubed to the fifth. This is a really, really nice composite function to begin working with. First of all, because it's the pieces are all very straightforward. Something cubed, something the fifth. We have a couple power functions that are interacting. Power functions are nice, they're simple. It's also very nice because if we wanted to, we could just simplify this. This is the same as x to the 15th. If you want a derivative of that, you get 15x to the 14th. So we know from the start of this exactly what the correct answer should be, and we can now sort of play with this in pieces as a composite function to see how these pieces need to fit together with the chain rule so that we end up at this, which we know is the correct answer. It's a great way to explore things. So, individually, what we have here is an inside function, which is x cubed, and the derivative of that is 3x squared. We know that, no surprises there. The outside function, here's a little piece of Dave-specific notation that I'll introduce. This isn't endorsed by any calculus textbooks. It's very idiosyncratic. But I represent the outside function using a big blob. Something is being raised to the fifth power. Whatever that something is, I don't know. It's being raised to the fifth power. The derivative of something to the fifth power is 5 blobs to the fourth power. So these are our individual derivatives. Derivative of something to the fifth is 5 somethings to the fourth. Derivative of x cubed is 3x squared. We need to combine these pieces somehow to end up ultimately with this thing. But before we start combining things, I want to talk about this blob. This blob is notable in that this blob has to be the same thing as this blob. If this were an x, this were x to the fifth, the derivative of that would be 5x to the fourth. This x has to be the same as this x. Taking a derivative is changing the coefficient, it's changing the exponent, it's not changing x. This x is the same as this x. This piece hasn't changed. And the same is true of our blob. When we do the chain rule, the blob never changes. So this blob here, when we started, this blob was an x cubed. So whatever we end up with, this ought to be an x cubed. The blob never changes. Blob to the fifth, derivative is 5 blobs to the fourth. It's got to be the same blob. But that doesn't change when you take a derivative. It stays x. This piece simplifies. Let me not use an arrow for that. Arrows are for derivatives. This piece simplifies into 5x to the 12th. If you just do the x cubed to the fourth, that's 12. So I know that this should be a part of the answer. If I want to get to this piece here, I need my coefficient to be 3 times larger, and I need 2 more x's to go from 5x to the 12th to 15x to the 14th. 3 coefficient, 2 x's is exactly what I have here. So the derivative f prime of x should be this derivative of the outside, say outside prime, which is 5 blobs to the fourth, multiplied by the derivative of the inside, which is 3x squared, and the blob never changes. It used to be an x cubed, still an x cubed. This will get me my 15x to the 12 plus 2 is 14. So that's how we can use this chain rule to get a correct answer here. I'm going to do another one using sort of a simple example that we can simplify into something that we know what the correct answer is before I start to do weirder, different things. Let's do something a little weirder. Let's do f of x equals, I'll say the square root of x to the fourth, which is the same as x to the fourth to the 1/2 power. A huge part of doing calculus at this stage is recognizing that radicals are fractional exponents and fractions can usually be written using negative exponents. If you can turn everything into exponents, you can use the power rule and then things get really simple. Don't try to take a derivative of square roots, that's a mess. Take a derivative of something to the 1/2 power. That's nice. So this simplifies ultimately into x squared, and the derivative of x squared should be 2x. Nice and straightforward. Let's see what the pieces look like if we do this one piece at a time. Inside function is x to the fourth, and the derivative of that is 4x cubed. The outside function is something to the 1/2, and the derivative of that is 1/2 somethings to the negative 1/2. These are just from the power rule. But again, we should be extremely careful to remember that the blob never changes. This was an x to the fourth in the original function. It's got to stay an x to the fourth when we do that outside derivative. Blob doesn't change. This blob is the same as this blob. So this piece equals, if I try to simplify this x to the fourth and then to the negative 1/2, I should get 1/2 x to the, I would multiply those, so I get -2. So this outside piece simplifies ultimately into 1/2 x to the -2. Let me pause on that for a second to talk about f prime of x. According to the last example we did, we can get the full derivative of the chain rule by multiplying these pieces together. So it's the outside derivative of the outside times the derivative of the inside. It's outside prime, inside prime. These look like ones. They're not. They're primes. This is derivative. Maybe I should use d's instead. Derivative of outside times derivative of the inside. There you go. So the derivative of the outside is going to be 1/2 x 4 to the -1/2. Derivative of the inside is 4x cubed. If I multiply these things together after I simplify this one simplifies into 1/2 x to the -2. So the 1/2 and the 4 should simplify into a 2. And the x to the -2 and the x to the 3 should give me an x. And I have the correct answer, or the answer that I know ought to be correct based on simplifying the original problem. So this is the chain rule. When you're looking at a composite function, I want you to identify the inside part and the outside part. Use some weird placeholder for when you're talking about the outside part. Don't put an x here, that'll be really confusing. Just use like a blob or a smiley face or an empty box, or I don't care what symbol or shape you use, as long as it is a placeholder that you're not going to confuse with the actual independent variable from the function. So anything except an x, I'm fine with. So you have the inside and the outside. You take the derivatives of those things individually. In this placeholder, you have to put the original function because the blob never changes. And once you put the original function back in here, you just multiply these two pieces together and you have yourself the correct derivative for your function. I'm going to cut this video right here. In the next one, we'll do some more exciting examples, and we'll talk about why it's called the chain rule.